Yeah, let's start. A few words about me. Although I got already a short introduction, I have about 5 years in exchange trading only as a software engineer, a few more years in other industries, and if you want to contact me, feel free after the talk. I'm also here tomorrow. And yeah, short description what we'll go through. It's quite a lot, but you can find it later on in the repo. What's the motivation if you want to build a trading system by your own? A few fundamental trading concepts we will need if talking about a trading system. Then some requirements, because yeah, we want to structure our approach, how we implement actually trading strategies, how we make our components communicate with each other, a little bit about market data, a little about placing orders and data storage, and last but not least, an outlook, how you can take this live or what you should think about if going live with this. So first of all, motivation, of course, trading, you want to make money. Then the access to markets is actually now easier than ever, especially to crypto. You have more control and flexibility than if you use some bot providers platform. It's actually a quite interesting exercise because there are different technical challenges that we will go through, and there are a lot of job opportunities. I don't know whether you know it, but the biggest paychecks you can receive are actually from high-frequency trading companies, but also it's quite hard to get in. And of course, self-made is always better than just using somebody else's software. So some fundamental trading concepts. What is trading? It's the activity of buying and selling things. This can mean that you buy apples and pay in pairs, that you sell stocks for money, or that you buy Ethereum coin for Bitcoin. What's an exchange? An exchange is actually a physical or electronic platform or location that you can use for trading. So for example, it's also called market. And examples are weekly markets in the city center, a stock exchange, or a crypto exchange. Algorithmic trading is trading on international stock exchanges using computers that have been programmed to buy or sell according to fixed rules. These fixed rules are your algorithms, of course. It's not only about stock exchanges, but also used for trading crypto or commodities, for example, electricity. Usually orders and order books are used for trading. Okay, so what are these? Order book is actually an electronic list of buy and sell orders, and for a specific instrument organized by price level. Okay, let's go through this bit by bit. An order is an offer to buy or sell something. And you can think about it a little bit like if you also have somewhere a whiteboard up and you just put up that you want to sell something and you put a price for 1 unit and how many actually you want to sell. And the order book is actually the whole whiteboard for one specific good. Order book level will be important in a little bit, but for now just memorize, okay, it's the aggregated quantity of all orders for one price. And I have here an order book example. It's unfortunately a little bit small, but where is my, here. Yeah, but if you look at it, so this is buying, this is selling, and this is a Bitcoin order book. And you can see here that somebody wants to sell 200 coins, and the price for one coin would be this 80-something K. And the important thing is here, you don't know how many people are behind this order book level because it's aggregated to this price. So there might be one person buying these 200 or 5 people. And remember, order book is only about the offer of buying and selling. So if you find somebody that actually wants to execute your order, this is a trade. So somebody else matched your order and you actually bought or sold the thing you wanted to buy or sell. And also very important, the accumulation of all trades. So If you buy and sell around, you get a position. How much do you actually own of this thing that you bought or sold? And a short summary to have it all in one place. So order is selling or buying an offer. An order book is just a list of some orders for one specific good. A trade is that actually your order was accepted by somebody or you accepted somebody's order. A position is how much you have of this good. And just to stop calling it good, usually we talk about instruments, so financial instruments or crypto instruments. Functional and non-functional requirements. So what do we want to do? Actually, we want to be able to trade instruments with different algorithms on an exchange because we might have a few ideas how we want to trade. We want to get insights about how we trade it. And we want to improve our trading systematically. These are our functional requirements. The non-functional requirements that we actually need to fulfill for trading is, okay, we just said we want to trade on different exchanges. This means we need to stay kind of extensible and also scalable. We want to trade multiple instruments probably. If you're trading, you're usually not only interested in Bitcoin, but also Ethereum or other stuff. And we might want to use different approaches because we don't have that one algorithm, but multiple other approaches. We want and also have to recordings about our performed actions due to transparency and compliance reasons. And we need to be sufficiently fast to trade properly. There is usually an offset, something about like if you trade smart, you don't need to be fast, or if you trade fast, you don't need to be smart, but there are certain thresholds you need to meet usually. The technical requirements that arise from this are usually, or in this case, okay, for trading, I need an API to receive market data to know what's happening on the market. I need an API to send orders because I want to trade. I need an API to receive feedback about what I send as an order and also about the trades I made. And I want to structure my components independently to connect them in multiple ways. So this is about what I said, using different algorithms on different exchanges and also for different trading instruments. To have records about the performed actions, I need to store what I did somewhere. I need to store what my actions triggered, so the outcome. These can be trades or that orders were cancelled for some reason. And I need to store what happened on the market. And to be sufficiently fast, I want to structure my components somehow to be able to scale them independently. You might have markets with a little bit more volume. You might have markets with a little bit less volume. So keeping them independently helps here usually. Pick fast technologies, whatever that means. And pick a location as close as possible to the exchanges. So this means really the hosting. This can be quite difficult as a normal person. For example, if you want to trade finance, because you won't get as a private person into the data center of etc. But for crypto, it's actually doable quite nice. And now the architecture, if we think about all these actually non-functional requirements that we come up with, is something like this. And now in the next steps, we'll go step by step through this architecture and how we might implement it. Short disclaimer, this is a proof of concept, so it demonstrates the typical architecture that I saw in some places and that also a lot of companies implement. Of course, in this proof of concept, I'm, for example, using Python. With bigger teams and more resources, you probably would do things differently. You would pick other technologies. And yeah, for the proof of concept, a crypto exchange was chosen, in this case, Kraken Futures. And most exchanges have some kind of simulation environment, so you can run your software there for testing purposes. Okay, let's start with the trading strategies, because this is your basic idea that you have, right? You have some approach in mind, and this is the part we're talking now about. What are trading strategies? So, or what they do? They, based on a signal, make a decision, and that they want to act on a specific market. They, the most important signals that they react to are usually market data, so what's happening on the market, the feedback that they get to their own orders, so a trade happened or nothing happened, the own position they have, they know how much they can sell or buy, and for derivatives, so stuff like futures, the data of the underlying asset. If you're trading an electricity future, you might want to be interested in the actual electricity price. And yeah, of course, this trading strategy needs to be able to execute the wanted actions on the market, and this means that there should be some kind of order actions. For the implementation itself, it makes most of the time sense to separate what you trade per instrument, so that you have really one instance of a trading strategy that only goes to one order book, because they are separate per instrument. Orders are usually also sent per trading instrument, so you cannot buy BMW stocks in a Volkswagen order book. And what a strategy has to keep in mind to make actually decisions, of course, the market data or the order book of the traded instrument. For this, it needs to get the actual exchange and do some book building. And what are the own orders that the strategy has currently on the market, because maybe it shouldn't act multiple times if it still has some active orders on the market. The own position, so how much Bitcoin, for example, do I have? Do I want to buy more? Do I want to sell maybe something? And also this, of course, if you think about Bitcoin, if the price goes down and I own 50 Bitcoins, also my risk is quite high to lose a lot of money. And we need, again, an interface to send order actions. So for this purpose, for the strategy itself, I implemented, or in general, in the proof of concept, I used a lot of separate functions. Of course, you can and should, where appropriate, use object-oriented programming, but I went mostly with quite some functions, and also I used a lot of multiprocessing, so the queues that you see here are usually multiprocessing queues. And yeah, for the strategy, I provided just a single function that has this signature, and it does something. What it does, we'll get into. And we have an interface to send some orders. So this means that the strategy actually can call this function to send some new order. It provides all the data that is needed, the price you want to buy or sell. Actually, do you want to buy or sell? And the amount, and then you can also modify what you actually have already on the market or cancel your orders. And then you want also to get information about what is happening with my own orders on the market. And yeah, here I also have a subscription function. I keep these very raw because you can have a look at the repo afterwards, otherwise time-wise it gets hard. And also because it's important, of course, to get for our strategy. As we talked about this middle part, it's important to know, okay, how do we get actually all the information? Because this is still communication in our system. And to allow for redundancy, so if some components fail, I decided here to go with horizontal scaling, and this requires communication via network. If you go for vertical scaling, so in the same system, you can of course use Unix sockets. This is probably the fastest way to make your software communicate on a single machine. And to send something via network, as we need it here, we need to serialize the data. And serialization is basically converting something into bits and bytes or back into the original object. And of course, there are some possibilities. Everybody in the room here knows probably JSON. Then there are protocol buffers, also called protobuf. There are flat buffers, which are just like the newer protobuf. Then there's MessagePack and, of course, Python pickle or some proprietary serialization that you can think about. Of course, there are a lot more possibilities, but these are just a few ideas. And if we have now serialized our data, we want to send it via network. So how do we send it over the network to the other components? And there we have also a few possibilities. For example, some proprietary TCP protocol, some proprietary UDP or even UDP multicast. I would recommend highly against it, only if you really need the performance, because it's really a pain to debug UDP multicast. Wasted a lot of hours of my life to that. You could use REST via HTTP. You can, of course, use gRPC, but that requires a protobuf as a serialization. You can use some message broker like Kafka or RabbitMQ, or of course you can just make your software communicate via database, for example, Postgres, MySQL. You have one component inserting, the other one retrieving. And of course, here again, there are also a few more possibilities. Now, what I went with in this system is sending and receiving MessagePack via Kafka. Why Kafka? It's fast. If you have a proper Kafka setup. I just heard from somebody that they have a Kafka where they have a latency of 10 seconds, which is weird because we had a system sending Kafka messages from Australia to Frankfurt within like a second, 2 seconds maximum via some dark fiber. So Kafka gets really fast if you make it go fast. It's quite established, so there's support in all big programming languages. You can program consumers and producers in pretty much every programming languages. I use here the library Kafka Python. You can also book it as a managed service, so you don't have to operate it. And there are many people who have experience with it, so it's easier to hire if you, for example, are a company that's using it. It's quite resilient because you have it's a distributed system, so if one broker fails, there is still a mechanism for failovers. Messages can be replayed, which we'll come to later, why this is important and really useful. And it's scalable, so you have end producers that just produce your messages. You have another count of consumers, and this allows us, for example, for the data recording to store the messages that the components are sending around with a separate consumer. And this allows us also to have multiple producers on the same channel if we want to have a system that fails automatically over. And it doesn't require a specific serialization in contrast, for example, to gRPC. And of course, there are a few disadvantages. So sometimes often it's very useful to know in a distributed system whether the counterpart is gone, so failed or something. There is no built-in mechanism to know whether there are no consumers or producers on the other side, so you have to implement something by hand. And it has to be operated as a separate service. So with gRPC, you just have like your both components communicating here. It's really a separate thing that has to run. There are also a little bit more in-depth reasons in the GitHub repo. You can have a look afterwards if you want to. Why MessagePack as a serialization? So it allows the conversion of any objects to bytes and back. It's schemaless, whereas with protobuf, for example, you really need to define beforehand what you want to serialize for sending and receiving. It's fast if you compare it to JSON, for example, and also if you compare the size to JSON. It's quite established, so there are also libraries in every big programming language. Here in this prototype, I used OR MessagePack, which is, I think, has an underlying implementation in Rust, so it's really fast. And it's backed and used by really big products like Redis, Fluentd, Pinterest. And also here a little bit more in-depth discussion in the GitHub repo if you want to have a look. And this is actually the system we get out of it if we put Kafka in. Market data. So this is the part where we get the input for our strategies. And in general, market data is also called public data. Like I mentioned, there is one order book per traded instrument, so they are all separate. It's essential because only with market data, a trading strategy can know the prices and quantities that counterparts are willing to trade. Mostly, market data exists as a unidirectional data stream. With crypto, it's often WebSockets. For electricity, it's also often WebSockets. In the finance world, it's usually TCP or even UDP, multicast. Depends on the speed you get or what you also buy. There are different types of market data. So the smallest, the most non-detailed version, let's call it like this, that you can get is the level 1 market data. You only get for buy and sell the best prices. So you get the lowest sell price and the highest buy price. Then there's level 2 data, so you get the top n levels. If you think about, I'll show it in the image after on the next slide again. So you get the top, 10, 20 levels, so the best actually 10 prices for each side. And there's level 3, where I mentioned if you have the level data, then you don't know how many people are behind us. With level 3 or tick by tick or order by order data, you really get the orders from the other people. So it's the most detailed, but of course it has the highest volume. But yeah, can be useful if you want to really trade in depth. And usually also you get information about trades. So you get something like, okay, there was a quantity of 200 traded and the order book changed like this. So this is usually separate information provided. And yeah, as I mentioned, level 3 data has the highest volume, but usually you also have to pay the most money to get it. And if we look here again, then where's my cursor? There. Yeah, if you think about level 1 data, so this would be for sell only this price, for buy only this price. If you think about level 2 data, then it would be like this list, for example, and also on the top, this whole list. And if we think about level 3 data, then basically each entry here opens up a dimension where you get to know, okay, is behind this quantity of 200, are there 5 people, 10 people, or only one person that wants to trade. So how can we use this market data? As we mentioned, we want to trade with our strategies on different exchanges, and usually different exchanges, they have different protocols, so we want to decouple it, and pretty common is just the adapter pattern, where we normalize the incoming market data from some external to an internal format. And for this, we have the component that I showed you already on the architecture diagram, the market data adapter, where there are separate operations. Some are per exchange, so you can implement some kind of plugin functionality, for example, and some common functionalities. And for example, it's usually separate mechanisms how you actually receive the data, so you want to keep this separate, different subscription types, etc. Then also there is the format the market data comes in is also per exchange differently. So you normalize the market data to some internal representation, and then common to all exchanges, you want to forward this normalized market data to your trading strategy. And if we look a little bit more into detail about the exchange we picked here, then we subscribe to the market data for different instruments. We get the data via exchange. The exchange sends us JSON. We use OR-JSON for fast parsing. And we get level 2 market data, so we get the order book levels. And on Connect, a snapshot is provided, so we get, like a snapshot is the whole order book, and then the consecutive messages are just deltas, so we get what changes in the order books, just because if you would get every time the snapshot, of course it's a lot of data, but if you get the snapshot at the beginning and then deltas, you do the so-called book building, where you keep track of the order book yourself. And yeah, basically this market data adapter, it receives the market data, it processes it, and sends it to strategies. But in this case, we do not only transform, but the market data adapter itself keeps also track of the order book. So already here some book building done, not only in the strategies, just to have some recovery mechanism, because if our strategy fails, we don't want to have to restart our market data adapter. So internally in our system, we send every n minutes a snapshot to the strategies, so the strategy can process it or ignore it. And yeah, how this looks like is this is what we get from the exchange. This is just the snapshot, some JSON this is Ethereum US dollar order book, and some sequence number, a timestamp, and then the both sides of the order book. And this is the outcome that I modeled with Pydantic in Python. And if we look at the delta message, it's a lot smaller because we really only get the information, okay, on the sell side, for this price, this is the new quantity. This means if the price already exists in the order book, we change the quantity. If the price doesn't exist previously in the order book, there's a new level. And if a level disappears, then in this case, in this protocol, the quantity is set to 0, so we know remove it from the order book. And this is how the internal representation looks like. Now, we also want to send orders with our strategy. And sending orders, what does it mean? Okay, we want our strategy to be able to send orders to different exchanges. Here again, different exchanges have different protocols, and you might come up with the same approach, use adapter pattern. And if you general words about order execution, or sometimes it's also called just order interface. Usually it's called private data because you send privately, only the exchange can see what you send, and you also get only information about the orders you send, not about the other parties' orders. It's usually bidirectional. You either send and receive via the same or separate channels. This can be, it depends again on the domain what's common. So for finance, TCP is pretty common. Then for crypto or electricity, for example, the input via HTTP, and then the feedback via WebSocket is pretty common. Yeah. And we introduced the order execution engine. So basically, this is the counterpart to the market data adapter, but on the backside of the strategies or on the outgoing side. We use, again, also the adapter pattern. And what happens is we receive a normalized order action, so just some internal representation of something we want to do from the strategy. And then there are, again, operations that are done differently per exchange. So you can implement, again, something like a plugin where each exchange is a different plugin that you can put in your application. And then for each exchange, there's some conversion to the actual exchange format from your internal format is done. Then the actions sent to the exchange. And if we receive feedback from the exchange, again, this feedback is normalized back into some internal representation. And this internal representation is sent back to our strategy, so the strategy knows what happened. And yeah, the order actions, a few words about them, they depend really on the market, what's possible. And the feedback can be quite different. And the most common ones that are used for order book trading that you can do is just place a new order, modify the price or the quantity of an active order if you change your mind, or to cancel the order. Again, if you use some different type of order than limit orders, usually there are a lot more operations. And the common feedback you can get is just some confirmations. So your new order was placed successfully, modify was successful, or your cancel was successful. Then you can get trades. these are usually called fills, so because your order was fulfilled, and an order, so you want to sell a quantity of 2, it can be a partial fill, so somebody buys from you quantity of 1, or it can be full fill, so somebody buys the whole quantity. And there are sometimes cancellations by the exchange for different reasons. They have a market outage, there are some compliance reasons, you hit a rate limit, whatever. Now, if we look to the exchange used in the proof of concept, then we see, okay, the placement of orders is done via REST. There are different endpoints for different actions, and JSON is expected as input, or as I noticed, also URL encoded works. And the feedback you can get either via WebSocket subscription, or by polling some REST endpoints, or also for the, I don't have it on the slide, but you get also some first feedback via the REST response. But I chose to keep it simple, the WebSocket, because you subscribe, you get updates. And the WebSocket endpoint that's used here is also the same as the one for the market data adapter, but just the subscription changed. And you get also a snapshot on the subscription, and then you get deltas, which in this case means you get at the beginning a snapshot of all the orders that are currently open, that you have open already on the exchange, and also a snapshot for a certain amount of time of all the fills that happened, which I didn't use here, but can be useful. And yeah, basically the order actions are received from the strategy and then forward to the exchange. And the same for the feedback, but vice versa. Feedback is received from the exchange, is normalized and forwarded to the strategies. And if we look at actually at what we send, so here we have again some order actions defined as pydantic models, and then how the request can look like either as URL encoded parameters or as JSON sent to the exchange. This is for a new order that you send. And then this is a fill response message that gets sent to us via WebSocket. And you see here some username you get. You get also an indication what you actually got from your subscribed feed. And then there's a list of fills, which I modeled like this, because I process the fills separately. So yeah. There are a few problems with orders. So order actions can fail for various reasons, because you have to imagine you're communicating with a different system. Everything is happening at once. So if you want to cancel an order, it could be already filled, but the response didn't arrive on your side yet. If you want to modify an active order, it could be already filled, but response didn't arrive on your side. It could have been cancelled by the exchange. And yeah, strategies might react too late or too early to stuff you do. Low latency helps here, but you have to factor that in if you implement your strategy. Actually, we had also some strategies that we implemented that were just reacting too fast, so the market couldn't keep up, and we really had bad trading results because we got some problems we wanted to modify, but the market didn't send us yet that we got already full. Then there are some restrictions regarding rate limits. So most of the times your actions per time are limited, and you're punished, or you cannot act if you violate them. There are often ways to pay more to get higher rate limits, or use multiple accounts, or often you even have the combination. For example, in finance, if you buy higher rate limits, usually you have to put a second account in. This makes really handling complicated because you then only can trade the orders from your separate accounts with that. To proactively do something against it, of course, your order execution engine can at least keep track of the orders. So It doesn't send cancels for already filled orders. It keeps tracks of the rate limits, and yeah. Data storage. So there are basically two different types of data, if you think about it. There is during live trading and outside of live trading, and due to time I have to speed up here a little bit. But basically during live trading, this is something that you need to know when you trade. Usually it's the most recent data and the volume is quite low because you don't have to keep book of so much stuff. And an example could be the currently active orders. Outside of live trading, for analysis purposes, usually you have quite a lot of historical data. The data doesn't change anymore and stuff, or examples are market data for backtesting. Live trading data, of course, you can use some database management system like Postgres to keep track of it, write the most recent states, retrieve them, and yeah, it's one more service in our context here to operate. You can also use Kafka, where you publish your most recent state regularly, and then if something fails, you can read it back again. And yeah, retrieval might get finicky because you have to locate, okay, what's my latest message? For the POC, I didn't implement any of them because, unfortunately, the scope got a little bit bigger of the POC, so bear with me. But in this case, I would probably implement the Kafka approach. Outside of live trading, we have to think about that our types of consumers and the analysis systems, they can be quite different. So the format that we choose must be independent of the language. There are different types of data, so it must be flexible. We have a big volume of data, so it must support compression. Of course, everybody probably knows here what comes next. Parquet is the thing to choose. And there was really a nice talk yesterday about Parquet. I don't quite remember the name, but you have to look it up. But it's basically the standard for big data volumes, and it's supported by all big analysis systems. What you have to think about if you implement this in production, you have to keep the retention time of your Kafka topics, of course, really high enough to draw the data from there. And you can, for example, schedule just data dumpers to dump data regularly from your Kafka topics, so you get all the information. This was the advantage that I mentioned that we get if we really take Kafka here. And I will skip here ahead a little bit to the outlook. So there are a few things we have to consider technically, of course. We have to implement that our POC is configurable because I hard-coded the plugins. There are no tests in the proof of concept yet, and you should test because you can lose a lot of money really fast. There is a Knight Capital, which was a big trading company that lost quite a lot of money very fast. You should implement logging and alerting. You should think about where to host it. Like I mentioned, finance mostly on-prem. Crypto is actually mostly in cloud, so you could choose a cloud close to them, close to the exchange. And how to handle emergencies, so how to keep risk and manage it. And keep in mind it's often better not to trade if you're unsure than to trade wrong. And fine-tuning depending on markets like timing and latency I mentioned, and also how much data you need to store. And business-wise, understand the markets that you're using, because otherwise you probably won't interpret your data and your strategy will not perform. There are different types of traders and grades of professionalization. This also reflects on the behavior on the market, different latencies, and there are also different compliance requirements depending on the market, because yeah, if you trade finance really professionally, maybe BaFin comes around and wants to talk to you. Yeah, thanks for listening, and this is the report. And I think I have 30 seconds, so maybe I will use them before we start with the questions, because we can have a short look whether we can get the software to trade. And it's too big, right? Ah, okay, no. You can check it out in the repo.
So thank you for the talk.
Thanks.
There are several questions. The first one is, how high does your trade frequency needs to be to hit rate limits of the exchange?
It depends on the. It depends really on the type of trades, because we saw we saw in some trading systems really that 360 actions per minute are already rate limited then, and this you can easily achieve with Python. And sometimes we saw that we had rate limits of 8,000 actions per minute, which we had a hard time to hit with even C++. So it depends really on the market and on the broker, because yeah, they want to get paid to fulfill your actions. So yeah.
So okay, thanks. So the next question: what's more lucrative, code a trading bot for yourself, hopefully making your money, or work as a coder for a high-frequency trading company receiving paychecks?
If you're technically really good, I think at the really good companies like, what are they called, Jane Street or something in the US, 800K is possible as a developer, but it's impossible to get in. But if you have a good trading idea, a bot is usually a good idea. I don't have good trading ideas, so I'm more concerned about the technical details. Yeah.
Okay, so next question. How do the strategies themselves materialize in code? Is there a DSL for expressing them?
Most of the times I saw actually people implementing the strategies just in Python or C++. So usually there was some abstract strategy class, and then they had an on-market data, and then there was stuff done. So there's no DSL, at least not in this system. Of course, there are bot providers that probably provide a DSL.
Okay. Can a trading platform be profitable against major high-frequency hedge funds with cutting-edge hardware-optimized co-location and direct market access?
It depends what you mean with lucrative, because like I mentioned somewhere, if you're really a high frequency trader, usually they use FPGAs, so they are really fast, but maybe not smart. And but crypto, for example, only really got professional in the last few years. So I think in the last few years it was still quite possible. And I know from a person who just click trades, so really at his broker, but he has an idea how to trade some stuff, and he's slow, and he's still leading a company. So if you have a good idea, sure.
Okay. So how do you manage to be physically close, reduce latency to a crypto exchange?
You can find out for a lot of exchanges in which cloud they are hosted, and then was it Binance? I'm not sure. Some clouds are, for example, in AWS Ireland, so you choose, of course, this as your region, and then you hope that you get close to them. And there are a few approaches, and usually you can find out where they are hosted.
Okay, I think the next question is basically the same, so let's skip it. So do you have a good suggestion on how to work with options data, given the odd nature of options, change in strikes, open interest, creeks, etc.?
To be honest, not from the top of my head, because you have to keep track of so much, like you said. No. I know actually that when we implemented options at one of the companies, it was really pain, and we sat there with like 5 people who had experience in some market data protocols of different exchanges, and it was still pain.
So there's 1 minute left for one last question. Just for a scale, what is the amount to computing power needed to run some examples of popular trading algorithms?
It depends what your strategy keeps in its head, right? Because usually you want to react fast, so you keep everything possible in RAM. So yeah, and then I think the highest volume that you get is from market data, and then yeah, there are approaches that you can run really a few algorithms just on a 4 gigabyte machine, because they don't keep anything in their brain, in their RAM. And there are approaches where we had just 100, 200 trading strategies running on a 200 gigabyte machine, and it was still not enough. So yeah, it depends.
Okay, thanks. One last question, yes or no. So are you a millionaire now?
No.
So let's thank him again. Thank you for the talk.
Thank you.